Okay, so can you hear me decently, at least?
Yes.
Okay, perfect. Let me, then start again. My talk today is about fractional calculus-based electromagnetic modeling of dispersive dielectric materials. This is an outline of my presentation after a brief introduction. So we'll dive into the finite difference time domain model used to solve Maxwell equations in dispersive media. We'll validate the model and apply that to a few complex examples before drawing some conclusions. Dispersive materials occur in different fields of science and engineering. So among those, I can certainly mention, the applications, medical applications that Jon was also referring to, such as electroporation, hyperthermia, and in general, evaluation of specific absorption rate in biological tissues exposed to RF radiation. Another relevant application is relevant to the material characterization for disordered dielectric media, such as polymers or biopolymers, emulsions, and microemulsions. So that obviously constitutes a significant challenge when it comes to evaluation of electromagnetic fields interaction. So for our purposes today, for this talk today, I want to focus on ground penetrating radar. So ground penetrating radar provides an effective means for non-destructive diagnostics in several contexts, such as survey of buried utilities. Think about different type of pipes in urban environment, as well as in the detection of landmines. And the same methodology, underlying methodology, can be also applied to the investigation of different type of terrains, so for avalanche prevention, as well as for the assessment of the structural integrity of different type of constructions, buildings, bridges, and the like. In order for a GPR, so ground penetrating radar surveys to be successful, it is important to have an accurate knowledge of the electromagnetic wave distribution excited within specific ground, a specific soil under RF exposure. And this in turn requires a knowledge about the physical properties of the soil being surveyed. That is affected by several parameters. Such as the composition of the soil. Think about different type of materials, such as soil, clay, and the like. Their composition, their geometrical structure, whether disordered or layered, multi-layered, and among all these parameters, the amount of water stored in the soil constitutes a significant driver into the frequency dispersion behavior of different type of soils. Affects significantly the relaxation processes occurring into a given material. Frequency dispersion in dielectric media can be modeled using the canonical formulations that are reported in this slide. So starting from the Cole and Cole-Davidson models shown on the left-hand side, as well as their generalization introduced by Avrilyak, Negami, and Raiku. So that are shown on the right-hand side. So you can actually notice a significant a growing complexity of the models moving from left to right. Complexity that is introduced obviously to describe the behavioral features of dispersive media in progressively more accurate way. So all the models reported here depend on given relaxation time, tau, and in the various expressions, one can recognize the epsilon sub infinity that defines the relative permittivity of the medium at infinite frequency, and whereas the quantity delta epsilon represents and denotes the difference between the asymptotic relative permittivity and the static permittivity, so at frequency 0. Obviously, another observation one can make is that all these models rely on fractional expressions. So fractional expressions dependent on the coefficients alpha, beta, and gamma that are all between 0 and 1. So this is an important observation because the time domain solution of Maxwell equations coupled to the models we saw on the previous slide can actually pose significant challenges. So, and one way that has been historically and used in literature to circumvent this complexity is by approximating the relative complex permittivity function of dispersive media by rational or polynomial function, this leading to auxiliary ordinary differential equations. However, this methodology leads to unavoidably inaccuracies associated with the approximation of the actual fractional behavior of the considered media. So we want to obviously reduce this type of and eliminate actually this type of limitation and approximation, and our purpose today is actually to show how to plug fractional differential operators directly into a FDDD scheme. FDDD stands for finite difference time domain technique, and is a well-known algorithm and methodology to solve Maxwell equations. So in this way, we'll be able to remove the source of inaccuracies due to the approximation I mentioned previously altogether. And while doing that, we'll be considering a generalization of the dispersion models, frequency dispersion models I showed previously. So with Raiku being, let's say, the more complex, formulation. And to this end, we'll be using a multi-relaxation model with the pole zero dielectric response that is shown here on this slide on the left-hand side. So where one can recognize the linear combination so of R fractional rational terms capital omega sub I over capital Xi sub I, where capital omega and capital Xi in turn feature polynomial fractional polynomial expression that is reported on the right hand side. So polynomial expressions dependent on coefficients capital A and capital B with orders alpha sub I and beta sub I. And capital R is in this case the number of relaxation terms that we are going to consider moving forward in our formulation. So we want to obviously evaluate the electromagnetic field distribution excited within dispersive medium, featuring the complex permittivity response shown on the previous slide. So we start from the Ampere law in differential equation. And by combining the expression of the complex permittivity into into the Ampere law, we end up with the expression reported here that can be also written in terms of capital N polarization currents, where each polarization current, capital J sub I, is in turn dependent on the electric field distribution and the fractional rational terms that were introduced on the previous slide in our model. So also important to mention here that sigma is the static ionic conductivity that is displayed by the considered material. So by transforming in time domain, so we then obtain the expression reported here at the bottom of this slide, where one can recognize model-based fractional derivative operators deriving from the anti-Fourier transform of the capital sub I and capital Xi sub I terms we have in the expression of each polarization current term. So we'll, for sake of conciseness, we'll be referring to each of those model-based fractional operators with the terminology and the notation reported here for the individual polarization current term and for the electric field capital E. So let us consider the first model-based fractional operator acting on the individual polarization current term. What we want to do is to evaluate that specific term by making use of the Riemann-Liouville definition of fractional derivative operator, and by doing so, we end up with different terms, different integral differential terms that are reported here on this slide. Each of them dependent on a parameter nu sub I that is in turn dependent on the fractional order, differential order beta sub I. So in this expression, integral differential expression, we can isolate the integral term that will be referring to as capital I. This integral term can be in turn evaluated using a finite difference methodology. And after tedious algebra, but rather straightforward, I skipped all the relevant steps, intermediate steps here for conciseness. We end up into the expression reported here that is dependent on running some operator denoted by capital Xi that is introduced in order to make this expression computationally advantageous, computationally viable as we proceed through the time marching scheme that is the underlying, if you want, process into the FDDD algorithm. So once the individual capital I term is evaluated in the way that is reported here, we can actually move back and evaluate the general fractional derivative term of the individual polarization current. And to this end, we simply apply the conventional finite difference approximation of ordinary differential operator of order nu sub I. So the expression is reported here is a very well-known expression, and by combining the different equations, we obtain the expression reported at the bottom of this slide. And once we have such expression, so we can eventually go back and evaluate the model-based fractional operator acting on the individual current density, polarization current density term. So the expressions are a little bit ugly, but they can be easily implemented into a computer program. So the expression, the finite difference approximation of the model-based fractional operator on the polarization current is reported here. So we can do the same for the other model-based operator acting on the electric field, and what we end up with is the even more ugly expression reported on this slide, which can be easily solved by computer algebra. So it actually constitutes a equation of capital R linear a system of capital R linear equations, where capital R is once again the number of relaxation terms that we are considering in our model, and the solution can be done. Can be performed once and then used through the time marching scheme of our FDDD algorithm. So by doing so, we can evaluate the polarization currents, each polarization current and the electric field. And once the electric field is known, we can evaluate the magnetic field using Faraday's law. So at this moment, we are able to evaluate the electromagnetic field distribution at any point in time and space through within our dispersive medium using the FDDD algorithm. So the FDD algorithm, of course, requires a finite grid to be implemented. So our computers are finite in terms of resources. So in order to truncate the FDD grid, we use what is known in the scientific literature as UPML, so uniaxial perfectly matched layer. That is nothing but ideal absorbing material that is able to suppress electromagnetic wave propagation as electromagnetic fields impinges on it. So the the material is characterized by a certain tensor of permittivity tensor that is reported on the left-hand side, and the various parameters are optimized in order to enable most effective numerical absorption of electromagnetic waves. So the values are of these parameters are reported here for sake of completeness, including the thickness of the absorbing layer that is selected to be 30 cells, 30 unit cells in the FDDD grid. So we then validate our model. So the validation is carried out in 1D. Because we are able to solve Maxwell equations in an analytical way in 1D. So for the specific type of materials, this is unfortunately not the case already as we move from 1D to 2D. So therefore, in 1D 1D problems constitutes effective way for us to make sure that the model we have developed is actually accurate. To this end, we consider the illumination of a layered or multi-layered dispersive medium by a plane wave. So this is illustrated by the visual here on this slide that shows the space-time, if you want, this distribution of the electromagnetic field excited by a plane wave in the presence of a layered dispersive medium. So one can recognize the various field components, so reflected, incident, and transmitted through the considered medium. You can also notice on at the top and at the bottom of the computational domain the effect of the UPML termination, so that, as I mentioned previously, enable a nearly ideal absorption of waves. And this is important to simulate effectively the extension of the computational domain to infinity. So we consider here for the first test case a single layer medium with the characteristics and the parameters that are reported in the table on the left-hand side, and on the right-hand side we have the comparison of reflectance and transmittance characterizing the specific medium as evaluated by theory. So that is the black continuous line, and as evaluated using the model, the fractional based FDDD model that we developed, and those are the light gray dashed lines. So as you can notice, the agreement is pretty good. And this obviously witness the soundness of the model, the numerical model we have developed. A more complex test case is shown here, relevant to a triple multi-layered material, so consisting of obviously three different dielectrics with the dispersive parameters reported in the table on the left-hand side. So, and also in this case, the benchmarking of the developed FDDD technique with our analytical model is pretty successful. So accuracy is pretty good. So given these results, and after making sure that the model we have developed is is accurate. We can obviously consider more complex examples, that unfortunately cannot be solved analytically. This is a example relevant to the GPR, so the electromagnetic survey of subsurface. So subsurface containing a metal pipe. To this end, we consider electromagnetic illumination source, so described by a current filament with a Gaussian, a modulated Gaussian pulse described analytically by the expression here on the left-hand side. The visual on the right shows the geometrical configuration of the problem that once again sees a metal pipe buried into a soil made out of dispersive material. The electromagnetic source that illuminates the soil with buried objects is in the air region on the top. Yeah. The dispersive soil that we are considering here is a clay loam soil with a moisture ratio of 0.009. To this end, we are going to use a double relaxation model. With the fractional rational expressions, so dependent on the terms capital Xi sub 1 and capital Xi sub 2. It tells me that I have to speed up, but that's reported here. The model is obtained by fitting experimental data available in the literature. So this can be done also using dedicated techniques based on particle swarm optimization, but this is out of the scope of our talk today. And by using those parameters and the model we developed, we can evaluate the field reflected and diffracted by the soil and the pipe. So by subtracting the field reflected by the soil, we can isolate the field component diffracted by the pipe that is shown on the right hand side. Actually, by looking at the distribution of the diffracted field over time and space, we can also infer about the relative position of the pipe to the electromagnetic source used to illuminate the target. So the pipe itself, whether it's centered, as shown on the left-hand side, or it is off-axis, shifted on one side, as shown on the individual on the right. By looking at the time instant where the peak pulse is detected, we can also infer the distance, if you want, the depth of the target. So whether it's buried deeply, so into the ground. So this is the situation relevant to what is shown on the left, or is actually pretty shallow, and close to the interface of the ground with air. And this is the situation on the represented on the right, where one can also detect and identify different features, including either or higher order reflected wave contributions. These are important in order to understand, the characteristics of the pipe. So I'm going to speed up a little bit here. So we consider a pipe with certain characteristics, and we can evaluate once again the total field and the scattered field electric contributions. And if you look at this in time domain, we can evaluate the characteristics, the composition of the pipe by looking at the distribution and the behavior of the scattered signal. whether the pipe is empty or, on the other hand, filled with certain material. So, this is the basis for GPR surveys to extract information about different type of utilities in ground, buried in ground. So this leads me to the conclusions. So I've shown today how to plug fractional derivative operators in the FDDD scheme to model and characterize frequency dispersive material in an accurate way while overcoming limitations of existing techniques in the literature. Yeah. So thank you so much for your attention.
You want the CTO or we'll move?
Okay, perfect.